For introduction, bench vise is fit on a bench as the name suggests. It has a body, fixed movable jaw and a handle. Handle is mounted on the spindle and fit to the movable jaw. The movement of the spindle enables the movement of the movable jaw. Threads are cut on the spindle and act as a screw and incorporates movement of the movable jaw by turning off the handle. The body, fixed and movable jaw is made of cast iron. The jaw plates are fit with screw to the jaws. Grooves are cut on the jaw plates so that workpiece can be clamped firmly within the jaws. Jaw plates are made of hardened steel. The first objective for this assignment is to state the assumption of the system like dimension and data required in the calculation. Second, to draw FBD for each of the system of structure. Third is to develop equation of equilibrium to show the force act on the structure. Fourth, to determine the torsional force that will fail the structure. And lastly is to predict the factor of safety used in the design. This is the FBD for our product. We have two FBD. First is for body and second is FBD for the handle. The body consists of a fixed jaw, movable jaw, handle and spindle. The length of the body for the bench vise is 35 cm and the length of the handle is 24 cm. The diameter of the handle is 1.5 cm and the spindle diameter is 4 cm and the length of the spindle is 5.5 cm. For the second FBD is handle. So the length of the handle is same for left and right. This is 12 cm and we put same force for both handle left and right, that is 80 Newton.
From the structure, we have measured a few values like handle length equal 24 cm, diameter equal 1.5 cm, and material used is steel. We also assume a few values for this product like Young modulus equal 78 gigapascal, force 1 equal 80 Newton, force 2 equal 80 Newton, and allowable shear stress equal 18 megapascal. Next, after we have all this data, we need to find the factor safety for this product. First step, we use equation of equilibrium to find torque. The formula is sigma m equal 0 and we will get the torque equal 19.2 Newton meter. After that, we need to find maximum shear stress that will apply to this product. To find maximum shear stress, the formula is maximum shear stress equal Tc divided by J. That were T equal torque, C equal radius, and J equal polar moment of inertia. We need to find polar moment of inertia first before we can calculate maximum shear stress. The formula is J equal pi divided by 2 times C power of 4, and we will get the value of polar moment of inertia equal 4.970 times 10 power of negative 9. Now, we can find maximum shear stress. Maximum shear stress equal 19.2 times 0.0075 divided by 4.970 times 10 power of negative 9. and we will get 28.974 megapascal. Next, we also need to know the angle of twist that apply for this product. To find angle of twist, the formula is angle equal TL divided by JG, and we will get 0.012 radian. To convert from radian to degree, 0.012 times 180 divided by pi, and we will get 0.688 degree. Now, we can find factor safety for this product. To find factor safety, the formula is maximum shear stress that we have already found divided by allowable shear stress that we assume. That is 28.974 times 10 power of 6 divided by 18 times 10 power of 6, and we will get 1.6 factor safety. From this result of factor safety, we consider that it is safe because the safe factor safety is more than or equal to 1, and we will consider that fail if the factor safety less than 1.
Overall shear stress must be greater than average shear stress to make sure that the structure is safe and will not break after high force was applied. Based on our calculation, the factor of safety that has been calculated shows 1.6 in value. It shows that the structure is safe to endure force applied towards the structure because factor of safety must be bigger than 1. If factor of safety is smaller than 1, the structure will easily fracture and not safe to be used by community. Keep in mind that factor of safety does not imply that the safety is always safe and free from accidents. Stress of a part from the system or structure can easily change the stress distribution to the whole system if forces applied is higher than what it can take. So, factor of safety will let us know the maximum force that can be applied and always be prepared to not cross the limit. As conclusion, every structure has its own limit in enduring the torsional stress that produced after force is applied towards the structure, and it is called torsional stiffness. It can be determined by calculating the polar moment of inertia. Factor of safety can be determined after that by dividing the maximum shear stress and allowable shear stress, and the result will tell us if the structure is safe or not.
Cheers, here's to nothing, hold the tears. What for something can we drink?